Welcome to the fascinating world of statistics and probability. Today, we are diving into one of the most fundamental concepts in data science and mathematics, the random variable. While the name might sound like something from a sci-fi movie, a random variable is simply a bridge that connects the uncertain events of the real world to the precise language of numbers. Whether you are predicting the weather, analyzing stock market fluctuations at Wall Street, or counting the number of users hitting a Google server, you are dealing with random variables. To understand a random variable, we first need to look at a sample space. Imagine flipping a coin. The results are heads or tails. These aren't numbers, they are outcomes. A random variable, usually denoted by a capital letter like x, is a function that assigns a numerical value to each of these outcomes. For example, we can say x equals 1 if it's heads and x equals 0 if it's tails. This mathematical mapping allows us to perform calculations, find averages, and predict future trends. Formally, we defined it as x mapping from S to R. Random variables come in two main flavors, discrete and continuous. Let's start with discrete random variables. These are variables that have a countable number of possible values. Think of them as steps on a ladder. You can have 1, 2, or 3 children, but you can't have 2.4 children. Common examples include the number of cars passing through a toll booth, the result of rolling a die, or the number of defective iPhones in a production batch. In the discrete world, we use a probability mass function, or PMF. This function gives the probability that a discrete random variable is exactly equal to some value. For a fair 6-sided die, the probability of rolling any number is exactly 1/6, or approximately 16.6%. If we visualize this, we see distinct bars. In large-scale systems like Amazon's fulfillment centers, discrete variables are used to model inventory. You either have an item in stock or you don't. Now let's shift our focus to continuous random variables. Unlike discrete ones, these can take any value within a given range or interval. They represent measurements rather than counts. Think of them as a smooth slide instead of steps. Examples include the exact height of a person, the temperature in London at noon, or the time you wait for a bus. Because there are infinite possible values between, say, 1.70 and 1.71 meters, the probability of a continuous variable being exactly one specific number is actually 0. Since we can't point to a single value, we use a probability density function, or PDF. Instead of looking at individual points, we look at the area under the curve over an interval. The most famous example is the normal distribution, also known as the bell curve. Statistics show that about 68% of data in a normal distribution falls within one standard deviation of the mean. This is crucial for quality control in companies like SpaceX or Tesla, where precision in component measurements is measured in microns. To summarize the key differences, discrete is about counting, while continuous is about measuring. Discrete uses sums and probability mass functions, whereas continuous uses integrals and probability density functions. One of the most important tools connecting both is the cumulative distribution function, or CDF, which tells us the probability that x will take a value less than or equal to x. Understanding these concepts is the first step toward mastering machine learning, financial modeling, and scientific research. By converting the randomness of the universe into organized data, we can make sense of the chaos. References: 1. Gujarati D9, Basic Economics. 2. John E. Friend, Mathematical Statistics with Applications. 3. Miller and Miller, John E. Friend's Mathematical Statistics.